Right. We learned a few concepts on circles. We learned about tangents. Now, just a couple of remarks related to tangents drawn to a circle. One, if there is an external point P, then I claim that there could be exactly two tangents drawn to a circle. We wish to draw tangents from P to the circle. Let's see how many tangents could be drawn to the circle. See, one for sure, from an external point, this certainly is a tangent that could be drawn to the circle. Call it A. Let me refer to the circle as S. Right? Now, this is the center O of the circle. This is the radius R of the circle. Right? A property that we learned earlier, the tangent would be perpendicular to the radius at the point of tangency. In this case, A is the point of tangency, OA is the radius at the point of tangency, and PA is the tangent. PA will be perpendicular to OA, a property that we learned right at the very onset. Now, let me join the external point P to the center of the circle. This is 90 degrees. The angle PAO is 90 degrees. See, if there is an angle 90 degrees, then with PA as the diameter, I could have drawn a circle with PO as the diameter. With PO as the diameter, I could have drawn a circle with this being angle in a semicircle, isn't it? So a unique circle could have been drawn with diameter OP and passing through A. How about it, right? Very good. So which means with OP as the diameter, let me draw a circle. With OP as the diameter, let me draw a circle. Let me do a little better job than this. This is a circle. It doesn't look very neat, but take it from me. This dotted line is another circle with OP as the diameter, right? And it intersects the circle S at yet another point, call it B. Yet another point, call it B. Now, would you then mind believing that the angle at B, that means angle PBO, must also be 90 degrees? Why is angle PBO equal to 90 degrees? Because look at this dotted circle. In the dotted circle, OP is the diameter, and this must be therefore another angle in the semicircle. So this must be 90 degrees. Angle PBO must be 90 degrees. And OB is the radius at B. OB is the radius at B. Hey, which means what? PB perpendicular to the radius at B to the circle S. Therefore, PB must be yet another tangent that could be drawn to the circle. How about it, right? So, if there is a single tangent PA that could be drawn to the circle from an external point, then another tangent at B could be drawn to the circle from the same point. So, there exist exactly 2 points A and B at which you could draw a tangent to S from an external point P, right? I hope all of you register this. Now, just a few more remarks on tangents. So one thing, from an external point, exactly 2 tangents could be drawn to a given circle. Now, this is a circle, and I draw tangent at A, and I draw another tangent at B. There are 2 tangents that I draw to this circle from an external point P, a tangent at A and a tangent at B. suppose this is the center O of the circle. This is the center O of the circle. OA will be perpendicular to this tangent. OB will be perpendicular to this tangent, right? The radii at the point of tangency are perpendicular to the tangents. That's a property of the tangent. Now, let me compare triangle OAP with triangle OBP. Let me compare these two triangles. Now, these are right angle triangles. Do you see that? Angle OAP is angle OBP. Each is 90 degrees. Each is 90 degrees, right? Now, in the two right angle triangles, the side OP is common to both the triangles, and OA is OB. Why so? They are radii of the same circle. OA is OB. They are radii of the same circle. And therefore, from RHS condition, the triangle OAP must be congruent to triangle OBP. The two triangles are therefore congruent, which leads us to the following conclusion. They are identical in all respects, therefore, very clearly then, PA must be equal to PB. This tangent must be equal to this tangent. That means the lengths of the two tangents drawn from an external point to a circle must necessarily be equal. So, PA equal to PB. The length of the tangents drawn from an external point to a circle must be equal. That's one conclusion. Second, since these two triangles are identical in all respects, this angle, this is the angle that the segment PA subtends at the center, call it theta, must be equal to the angle PB, angle that PB subtends at the center. That means theta. That means the two tangents PA and PB subtend the same angle theta at the center of the circle. That's property 2. Also, very clearly, this angle must be equal to this angle, owing to, that means if this is alpha, this must also be alpha. Meaning what? The line joining the center to the circle, from the line joining the external point to the center of the circle, the line joining the external point to the center of the circle must bisect the angle between the two tangents PA and PB, right? So let me just list out the properties that we have learned. One, of course, from an external point P, exactly two tangents could be drawn to a given circle. Two distinct tangents could be drawn to a given circle. One. Second, the length of the two tangents drawn from an external point must be equal. PA equals PB. Tangents from an external point must be equal in length. Also, third property, PA and PB, the two tangents, subtend equal angles at the center. Isn't it? PA subtends an angle theta at the center, PB also subtends an angle theta at the center. And then we have the line joining the external point P to the center of the circle must be an angle bisector between the two tangents. Right? The line joining the center to an external point will certainly be an angle bisector between the tangents PA and PB. So now these are some properties that you must bear in mind, and you're ready to use these properties as and when required, whenever. Now, another property which would be of consequence in problem solving. Let me just communicate that property to you. So if this is a circle, and I draw tangents at two external points A and B, P is the point from which the two tangents were drawn, O is the center of the circle, then I claim that the line joining A and B, this AB is a chord. It's also called the chord of contact. AB is also referred to as the chord of contact. With respect to P, external point P, I claim that the chord of contact is perpendicular to OP. That means AB is perpendicular to the line joining the center to the external point P. This is my claim. Now let's see how easy or difficult it is to establish this proposition. Obviously, I would call this point M, say. Let me call this point M, say. Now, let me compare triangle MAP with triangle MBP. Let me compare these two triangles, MAP and MBP. Now, in these two triangles, realize that PA is PB. Why? These are tangents from an external point, must be equal in length, right? Also, angle APM must be equal to angle angle BPM. Why? Because the line joining the center to the point P must be along the angle bisector between the two tangents PA and PB, a property that I just mentioned a little while ago. So this angle equals this angle, this side equals this side, and in the two triangles, PM is common to both the triangles, and therefore SAS, two sides and the included angle, this side, and the included angle of the two triangles are equal. So from SAS condition of congruency, triangle MAP must be identical to triangle MBP. Right? Now, once this happens, then AM must also be BM. AM must also be BM. Right? This side must be equal to this side because the two triangles are congruent. And OM is what? OM is the line joining the center to the midpoint of a chord, and therefore must be perpendicular to the chord, right? OM is the line joining the center to the midpoint of a chord. M is the midpoint of AB. The line joining the center to the midpoint must be perpendicular to the chord. So this would really mean that OM perpendicular to AB, And if OM is perpendicular to AB, it would mean that OP, which is just an extension of OM, is also perpendicular to AB, right? So another property that we sometimes use. So get a hang of some of these properties, and we'll be ready for more problem solving, more properties while we continue our journey with circles. Thank you very much.